Welcome to the fastest way to learn data structures and algorithms. Today, we are diving into a legendary challenge, LeetCode 289, the game of life. This is not just a coding problem, it is a beautiful simulation of cellular automata. Mastering this in-place strategy is a massive level up for your array manipulation skills. We are given an M by N grid representing a board of cells. Each cell is either live, marked by a 1, or dead, marked by a 0. Every cell interacts with its 8 neighbors to determine its next state based on 4 simple rules. 1. A live cell with fewer than 2 live neighbors dies. 2. A live cell with 2 or 3 live neighbors lives on. 3. A live cell with more than 3 neighbors dies. And 4. A dead cell with exactly 3 live neighbors becomes alive. The catch? All changes happen simultaneously, and we must solve it in place. If we update the board directly, we lose the original state of the cells, which ruins the neighbor count for everyone else. To solve this in place, we will use temporary states to mark cells for transition. We will use the value 2 to mark a cell that was live but is now dying. And we will use the value 3 to mark a cell that was dead but is now coming to life. This way, we can still tell if a cell was originally alive by checking if its value is 1 or 2. Once we have marked the entire board, we do a final pass to flip all the 2s to 0s, and all the 3s to 1s. Efficiency? Constant extra space. Think of this like a city planner. A planner walks through a city, marking certain buildings for demolition, and others for new construction, based on local zoning rules. No building is actually moved until the entire city map has been marked. This way, the original layout of the city is preserved during the entire planning phase. Let's dive into the dry run. Look at the board. We start at row 0, column 0. This cell is dead. It has only one live neighbor, at 0, 1. Since it needs exactly 3 neighbors to become alive, it stays dead. Next, look at row 0, column 1. This cell is live, but it only has one live neighbor at 1, 2. According to rule 1, it dies from underpopulation. We mark it as 2. Now, focus on row 1, column 0. This cell is currently dead. But look at its neighbors, 0, 1, 2, 0, and 2, 1 are all live. With exactly 3 neighbors, this cell will come to life. We mark it as 3. Let's skip to row 2, column 0. It's a live cell, but it only has one live neighbor at 2, 1. It dies and we mark it as 2. Finally, look at row 3, column 1. It has 3 live neighbors in the row above it. It becomes live, so we mark it as 3. After marking the entire board, we perform our final sweep. All 2s flip to 0, and all 3s flip to 1. The transformation is complete. In our Python code, we iterate through every row R and every column C. For each cell, we call a helper function to count its live neighbors. Inside this helper, we look at the 8 surrounding coordinates. We count a neighbor as live if its current value is 1 or 2, because 2 means it was originally alive. Once we have the count, we apply our logic. If a live cell has fewer than 2 or more than 3 neighbors, we set it to 2. If a dead cell has exactly 3 neighbors, we set it to 3. After marking the whole grid, we run a second nested loop. We use the modulo operator, val%2, to transform our temporary marks into their final states. 0 and 2 become 0, while 1 and 3 become 1. Simple and elegant. For time complexity, we visit each cell exactly twice, once for marking and once for updating. That is O of m times n. For space complexity, since we modified the board in place using temporary values, we used no extra data structures. That is O of 1 constant space. And that is how you simulate the game of life with 0 extra space. If this visual breakdown helped you, hit that like button and subscribe to Leo Academy for more premium DSA walkthroughs.